Hi, this is Jason Baker, and welcome back to our lecture on DevOps practices. The second component of DevOps is automation, and we've already covered automation to a certain extent in this course. You know that we automate things in order to make our processes faster, more reliable, to scale our processes, and try to eliminate humans from our processes to try to eliminate mistakes. So our mantra in a DevOps organization is that we try to automate almost everything. We recognize that humans are fundamentally brittle and that the processes that we're trying to implement have to be repeatable. And that's where automation can play a major role. If you can automate something, then you can ensure that that process is performed the same way over and over again. And versus if you have humans performing a certain process, then humans are liable to make mistakes somewhere along the way. Automation allows us to very cost effectively scale our work. It allows us to reduce the cycle time of our processes and ultimately improve quality. One way to think about software development is looking at software development as an assembly line. And that's the way that DevOps organizations look at software development. They look at software development like an automated manufacturing line where we design our product, we determine our our application requirements, then we assemble the product, we write the code, we test the product using our software quality assurance practices, and then we package that product up into a release, and we deploy our application into a production environment. And during the software assembly process, work is moving through our organization. It's queuing up in different parts of the company. For example, your product team might be thinking up new features or new requirements for the product, and those features end up as stories on some sort of product backlog. We might have code that is stuck in a testing stage where our software quality assurance team is either manually or automatically testing our code. So our code is sort of moving through our development organization, and it's sort of queuing up in different parts of our organization, very much like products moving through a manufacturing plant. And in a manufacturing plant, oftentimes they use a Kanban board to sort of visually describe where work is located uh, within the organization, and to track work as it progresses through the organization. The same thing is true in a software development organization. We oftentimes use Kanban boards to show the queue of work. We'll have work that might be in a pending state and some sort of product backlog, and work that's moving through different development teams, and then onto the testing organization, then finally work that is deployed into a production environment. Well, the reason that DevOps organizations look at software development as an assembly line, once again, comes from the lessons that were taught to us by the Lean community. And there was a very famous proponent of Lean, and he was one of the first to really study Lean and bring Lean concepts over to the United States and Europe, and that was W. Edwards Deming. And he wrote that when we're creating these product assembly pipelines, we need to cease dependence on inspection to achieve quality and instead build quality into the product. And this is really a fundamental concept of lean. And many manufacturing organizations they follow Six Sigma principles, which is derived from lean. And the purpose of Six Sigma is to build quality into the product that's being manufactured. And what we've found in the software development world is that oftentimes companies that are building software products are focusing their time and effort on trying to find defects after the code is written versus preventing the addition of defects into the code while it's being created. And how do we know this? Well, if you just look at practices that are being followed by traditional organizations, you'll see that most of these organizations are engaged in a significant amount of manual exploratory testing of their software applications. They might be, doing some end-to-end testing. They may be doing user acceptance testing. They're testing their code after the code has been written to try to figure out if the development teams have written quality code or not. In a DevOps organization, we try to adopt a shift left lean alignment. And we do that in order to try to increase the focus on quality earlier in the development process. So what do I mean by this? Well, in your traditional organization, your the organization really isn't focused on the quality of the software code and the product until later in the software development lifecycle. The application developers are and teams are creating the application requirements, they're coding the applications, and then at some point they hand off the application to a software quality assurance organization, and that organization tests the code to see if it not only meets the requirements, but to see if it has any defects. In a shift lean alignment, we try to build quality into the product from the very beginning. So quality assurance becomes a developer's one of their primary missions. And you don't necessarily have an entirely separate organization that's devoted to quality, because the developers are really focused on building quality into the product, which means that you don't need to spend as much time and effort later on ensuring that the code which was created was quality code. Well, how do we put this into practice? What I found is that most organizations they have created most organizations today are really focused on manual exploratory testing and building automated tests. And typically they'll construct their quality assurance process in such a way is that they form what we call the ice cream cone anti-pattern in software testing. And that's this pattern on the left, where the developers may write a few unit tests to test their code at a functional level, but then the software team and the quality assurance organization is spending most of its time writing integration tests and creating this giant suite of automated tests. So oftentimes these automated tests are exercising some sort of graphical interface. They might be exercising like a web interface, These kind of tests are very expensive to write, very time consuming. They're also very brittle. And a small change in the application, especially in the web interface of the application, can easily break tests. And then finally, these organizations are spending a lot of time on exploratory testing, where they might have like an entire book, an entire suite of manual tests that they're running for each release. They have maybe thousands of tests that they need to perform manually because these tests haven't been automated yet. This ice cream cone anti-pattern that many organizations have created in terms of their testing processes, it creates a process which is very time and resource expensive, and the this isn't a process which supports high velocity releases. This sort of automated GUI testing and manual exploratory testing process, may require you to spend days, perhaps even up to a week, testing your software application. So the question is, how do these organizations that are releasing multiple times a day, maybe they're releasing every single hour, or they're releasing multiple times a week, how are these organizations able to test their software so quickly? And why is it that the software they release is generally higher quality than these organizations that are spending all this time and effort creating these massive suites of automated tests and manual exploratory tests? Well, it's because these organizations have basically turned this ice cream cone pattern upside down, and they've created what we call the ideal test automation pyramid. And so what they have done is they've invested most of their time and effort at the unit testing stage. And if you know anything about unit tests, you know that unit tests are the fastest types of tests to execute. You can literally run thousands and thousands of unit tests per minute. These are very fast, very efficient, functional tests. And the unit tests are typically written by the software developers. So again, when you think about the shift left methodology, instead of relying upon a separate software quality assurance team to write a bunch of tests to test the quality of the software that the developers are writing, instead the software developers themselves are creating the majority of the tests, and those tests are going to run very early and often in the software development process. So you're essentially trying to build software quality into the product while you're building the product. You're still creating the integration tests. You're still writing a few automated GUI tests, and you may have to do some very basic manual exploratory tests, but these represent a small fraction of the number of tests that you would typically write if were a traditional organization building this ice cream cone anti-pattern. Well, what does this look like in practice? Well, here's an example testing pyramid that you might find in, let's say, a Java application. In this case, the developers wrote a Java application, and it has 1,748 unit tests. Those unit tests are able to run in around a minute. There's also a set of JavaScript unit tests that they're testing some sort of client-side framework, and those tests run in about a second. Then there are 24 integration tests that are testing the integration between different components of the application, Those are more expensive tests. They run in 8 minutes. And then finally, there are a set of UI tests, user interface tests, and these are probably more like true end-to-end tests. These take 13 minutes. These are by far the most expensive tests. The key here is that the developers were able to build an application. They were able to build quality into the application early on because they focused on unit testing more than on the expensive and brittle automated testing, which comes later and after the code has been written. And because they were able to shift left, they were able to um, to build a testing suite that is able to run in this case, it looks like less than 25 minutes, which means that as they push code changes out, they're able to push these changes out probably at least maybe once every 30 minutes. So shift left allows us to improve the quality of our software because we are we're building quality into the product versus relying solely on inspection later on to discover the defects. The other big benefit of this shift left methodology is that it also reduces our cost to develop software, and it reduces risk. And this table might look familiar to you. You probably, if you took the introductory software engineering course in this graduate program, you probably saw a very similar looking table, and you learned that it's much easier for a developer to fix a defect when that defect is found during the unit testing process than when that defect is found much later on in the automated testing or manual exploratory testing, or even if the defect is found in production. Once that defect is released into production, it becomes very, very expensive to fix from a time and a cost perspective. And as somebody who's done development work for many years, I can tell you that once I've written some code and that code has been merged into the mainline branch of the repository and ultimately pushed out to a production system somewhere, I'm already I'm already working on the next feature. I'm already working on the next story. I've already pretty much forgotten the code that I had just worked on. And so to have to like do a context switch and go back to that code and try to fix something is oftentimes very time consuming and expensive. Another practice that is very common within DevOps organization is a practice called continuous integration. And the idea behind continuous integration is that it represents a software development practice where developers are continuously committing code changes to some sort of mainline branch within a source code repository. And the idea behind continuous integration originated as part of an agile methodology called extreme programming. And the idea, so traditionally, the way software development has been done for decades is that, traditionally software developers were writing code. They were writing code generally on a feature branch within a code repository. And so they would write their code, and then by the end of the day, they would check that code in, and everybody's code was all the developers' code was sort of mashed together at the end of the day, and a nightly build was performed. The idea behind the nightly build was to see if the software still works. And the challenging part was that you could be the developer that breaks the build. You could try to merge some code in that breaks that build, and then you'd be stuck there trying to fix it. The worst thing you could do was merge your code in late on a Friday afternoon, and then the build kicks off, and then suddenly the build is broken, and you're stuck there on a Friday night trying to get the build to work again. Sometimes what developers would do is, instead of checking their code in every night, they would just try to check their code in when it was done. And they might be working on that code for weeks and weeks. So the developer is sitting there working on the code. It's in their own feature branch, and they've been working on this code for weeks. And then they go and they check it in to the mainline branch, and then they encounter what we call merge hell, meaning that they're unable to merge their code into the mainline branch because other developers have been making changes which are inconsistent with the changes that they've made to their code, or they conflict with the changes they've made to their code. And now they have to spend all this time and effort trying to deal with all the different code conflicts. I worked with an organization a couple years ago where they had like four different software development teams, and each development team would go off and work on a separate set of features for their product. And they would generally work on these features for sometimes up to, say, 2 to 3 months. And then after each of these teams were done writing their features, they would spend generally 2 to 3 weeks just trying to merge all the code from those features together to try to get everything working together again. They would literally spend weeks, and they plan for it in their software development schedule. Weeks of time to try to mash all these different code changes together and get everything working properly. Imagine that type of organization trying to release code on a daily basis. It's simply not possible, right? I mean, they need weeks just to mash all their code together. So this idea of continuous integration represents a fundamentally different way of developing software. Instead of teams going off and writing software, writing a bunch of code, and then later on trying to merge this code together, what happens in an organization that's practicing continuous integration is that developers are continuously integrating. They're continuously merging their code with the new code written by other developers. So, and the end result then is that companies that are practicing continuous integration are able to deliver software changes much faster and with fewer bugs. And because those bugs are caught much earlier in the process, if there's some sort of integration conflict, you're going to find out about it right away. And people are in a great position then to be able to deal with those code conflicts because the code is very fresh in their memory. They worked on the code that very same day. So, what are some of the practices around continuous integration? Well, first of all, one of the key practices is that software developers, when they're writing code, they're checking in that code at least once a day to a single branch. And all of the developers are checking their code in to the same branch. So if you have like a Git repository, and that Git repository has a master branch, and you have a team of software developers that are writing code for your application, all of those software developers throughout the day are committing their code to that single master branch. And so as one developer commits code, the other developers can then rebase their code and pull in the changes made by the developer that committed work to that master branch. Every single time a developer checks their code into the single branch, that code generates and triggers a software build, meaning that every single change to our software code base triggers a build cycle. And every time we build the software, we perform a set of unit tests. We might perform a set of integration tests. And everybody involved in the software development process is able to view this software build and view the test reports that are being generated. And what this gives software developers is fast feedback. We're constantly asking ourselves the question, does our software application still work? And every single time we commit a change to our application repository, we're testing the software over and over and over again. We're testing to see if it still builds properly. We're testing to see if all the unit tests run properly. We're testing to see if the integration tests still work properly. And by testing our application after every single change that's made, we're able to quickly identify if there are any sort of quality issues. So contrast this with the traditional process where all of these changes get batched together and we're doing a nightly build. And at the end of the night, we're trying to see if our software is still working. And sometimes these changes that are checked in, these are code changes that have been worked on for weeks and weeks. And so the developer doesn't really know if the changes they've made are going to work in the software product until after all of that code has been written. Continuous integration gets us away from that traditional practice. We're making changes often, and we're checking those changes in as often as we can to see if our software still works. Well, you might be asking yourself the question, how can these software developers who are following this continuous integration practice, how can they check in their code on a daily basis? Because they might be working on like a new feature in a software application that may take like 1, 2, or 3 weeks to develop. So how can the software developer check in their code when the feature they're working on isn't even done yet? Well, that's a great question. And the answer to this is that software developers do in fact check in code for features that are unfinished into their mainline branch. And oftentimes those unfinished features are released into production. And this seems a little odd at first, but there's a pattern that has developed that allows us to do this successfully, and that's called the feature toggle pattern. And the idea is that we can work on code and work on features, and we can deploy these features into our releases even though the features are not done yet. The way we do that is by setting up a toggle, which is sort of like an on-off switch in our software, which allows us to hide and disable the unfinished features in a production environment. Meaning that our customers are still accessing our software and they're using it, but the features that we're working on and that aren't finished yet are just not visible. Our customers can't exercise that code or get access to that feature because it's been switched off. The beauty of this pattern is that It allows us to take this code which isn't finished yet and integrate it with our production code. And that allows us to test it in a way. We can ensure that we haven't broken any of our production features. We can do the automated testing and the manual exploratory testing to ensure that the software still works. So even as we're working on a new feature, we're testing to make sure that that new feature that is still unfinished, testing to make sure that that hasn't broken our software. And this is a very, very common pattern that some of the largest internet companies in the world have implemented. If you, you know, if you're, let's say you're a Facebook user, what you might not realize is that when you're accessing the Facebook website, you're doing that with your web browser. Your web browser there's a client-side application written in JavaScript that's running inside your web browser. That application already has the features that Facebook plans to release in the next 6 months running inside of it. So all the features that Facebook is planning to release, um, all that code already exists in your browser. It's already running there. It just hasn't been switched on yet by Facebook. And when they switch it on, they're not going to switch it on for all of their customers and users all at once. What they'll do is they'll turn that feature on for a small percentage of their customer base, say like 10% of their customers. And what that allows them to do is to sort of test out new features to see how customers respond to those features and to see what the performance impact is of those features. If and then gradually over time they'll roll out that feature to a larger and larger percentage of their customer base. So I've talked about continuous integration and the fact that every time a commit to a repository, a code is committed to a repository, that triggers the build of a software application and it triggers the testing of a software application. Well, the triggering of this build process and the testing process isn't done manually in a DevOps organization. And because, again, we try to embrace automation. And our mantra is that we want to automate everything we possibly can. And the way we automate the building and testing and oftentimes deployment of our software applications is by creating something called a code pipeline. This code pipeline represents the automated process for getting our software from the version control system like Git into the hands of our customers ultimately in a production environment. You can think of this as being a sort of automated continuous integration. And the beauty of code pipelines is that it allows us to enforce a certain set of processes in terms of the building, testing, and deployment of our software application. If you force every single code commit to go through a code pipeline, that means that it's not possible for code to make its way out into production and into the hands of your customers without having gone through a fairly rigorous testing process. So it really enforces the release and deployment processes in your software development lifecycle. It also speeds up the development and release process because our goal within a code pipeline is to automate each step of the pipeline as much as possible. And there might be certain cases where you need to do some manual exploratory testing, but in most every other case, we automate every single stage of the pipeline, which means that the software code changes are able to flow from our software code repository into our production environment much faster than if we were trying to sort of manually perform each one of these steps. We use continuous integration systems, software um, applications like Jenkins to manage code pipelines. Jenkins is a tool that we'll spend some time working with in the latter half of this course, and you'll see how it allows us to create different stages in a pipeline and where we can manage the build and testing and deployment of our software application. So I've talked about continuous integration. There's another concept which sort of dovetails with continuous integration, and that's this idea of continuous delivery. The idea behind continuous delivery is that it's this process which helps us ensure that software is always deployable throughout its life cycle. Again, think back to the traditional organization that's where developers are writing code on long-running feature branches, and after weeks of writing their code, they attempt to merge their code with the work of fellow developers, and they have to go through this really time-consuming, expensive process of integrating code changes with one another. Continuous integration seeks to speed up that process significantly because all the code changes we're making throughout the day are continuously being integrated and merged with those of our fellow developers. Continuous delivery then uh, ensures that whatever software code changes we're creating, that those changes are eventually going to be deployable. And the way it does that is by moving our software changes through a code pipeline. So if you look at this diagram, you'll see that the agile software development process, and let me get my enable my pointer here on this diagram. You'll see that um, in the software development process, we might use something like agile software development when we're planning the requirements of our software. We're creating something like stories. We're using agile development for coding and building our software. Then we're using continuous integration. We're using continuous integration to um, to merge all those code changes continuously throughout the day, and every time we make a code change, that automatically triggers the building of our application and the testing of our application. We call that process continuous integration. Continuous delivery takes this one step further. Continuous delivery ensures that not only does our software work in the sense that it's tested, but our software can be released. Our software is in a state where at any given point in time, we can release it to a production environment. There's actually um, one more stage, and that's called continuous deployment. It's not on this particular diagram. The idea behind continuous deployment is that once our software has been checked in to the code repository by the software developers, that software, that the code is put on the pipeline, and it's basically on this freight train headed towards production land, meaning that if the software code changes are able to pass each stage of the software code pipeline, ultimately that code will automatically be deployed. There will be no human being involved in the deployment process. If your organization is following this practice of continuous delivery, your software pipeline essentially ends at the release stage. So your software has been fully tested. It's perhaps it's been deployed and running in a staging environment, and you're running some smoke tests against that application, and you've essentially proven that your software is releasable. But then somebody is manually involved in triggering a deployment into a production environment. There's sort of like one last gate, which is a manually triggered gate. In a sort of continuous deployment process, there is no human being. There's no human intervention. Once the code has been checked into the repo, that code could end up in production automatically if it passes through all the different stages. So many companies today are practicing continuous integration to some extent, um, especially more modern companies that are following modern DevOps practices. Some of those companies are actually doing continuous delivery in the sense that they're able to deploy their application to a staging environment, and they're proving that their software is releasable. Very, very few companies today are actually doing continuous deployments where they've taken the human completely out of the loop, and once the software is committed to the repository, it could end up in production a short time later. So one of the other things I wanted to talk about briefly, and you've already read about this in the course, is this notion of infrastructure as code. And infrastructure as code is a really important concept, especially when talking about automation. Traditionally, when we built infrastructure, that infrastructure was built by hand. You had experienced engineers who would would manually sort of work with infrastructure and configure that infrastructure based upon whatever the requirements of the application were. And depending upon who was working on the infrastructure, it might be built slightly differently, each time. With infrastructure as code, we're basically building infrastructure using software. We're writing code, and that code is being interpreted by some sort of software application or some sort of tool, and that tool then is going out and building the infrastructure for us. And the beauty of that is that if we can create infrastructure using code, then that infrastructure becomes versionable because we can version our infrastructure code in a software code repository like Git. It becomes testable. We can use our code to stand up a test instance of our infrastructure, our test environment, and then we can run a battery of tests against it to see if that infrastructure does what we need it to do. And most importantly, that infrastructure deployment becomes repeatable. If we define our infrastructure using code, then we can stamp out identical infrastructure environments over and over again. So it becomes repeatable, and we can build infrastructure the same way every single time. The goals of infrastructure uh, are that the infrastructure as code allows us to change our environment very, very easily and very quickly. and change is no longer an obstacle within our IT organization. Infrastructure changes become routine because changing our infrastructure is as straightforward as changing our code, and we have all sorts of processes, mature processes around, how to manage code changes. We can take those processes and use them the same way when managing and maintaining infrastructure. And so, I talked about how our software development uh, teams use continuous integration, and how the code that they create goes through these code pipelines. And when I was talking about that, I was really focused mostly on, software applications. But the fact is that if we treat our infrastructure as code, if we treat our infrastructure like we treat software, then we can use these same practices when making infrastructure changes. We can actually we can use continuous integration, and we can create code pipelines through which our infrastructure code flows. Here's an example of a change management pipeline for infrastructure. In this case, infrastructure code has been submitted to the pipeline, and it's going to be linted. It's going to go through some sort of build process, and maybe unit tests are run. There could be an acceptance testing phase where a series of smoke tests or functional tests are performed. And then, ultimately it's going to go through other testing stages where, um, provisioning tests and staging tests are performed. So we can manage our infrastructure code the same way we manage our application code. The last thing I wanted to talk about in this lecture, and the third component of DevOps, are metrics. And metrics are really fundamental to the way we make decisions within a DevOps organization. In fact, DevOps organizations are really fanatical about collecting data. The idea is that, we never really know when we'll need the data, but once we need it, we're so glad and so thankful that we were collecting it. We collect the data from all kinds of different resources within our environment. If you've got like a production environment, we're collecting data from the underlying infrastructure that's supporting our application. So the computing nodes, so from the networking infrastructure, from storage infrastructure. We're collecting data from our applications, and applications today, they generate all kinds of different log information that gives us insights into the performance of those applications, and any sort of anomalies or error events that occur. We take all of this data, which is sort of time series and unstructured data, and we generally try to store those in some sort of centralized repository that we can easily query to identify trends and correlate different types of data. Our decisions are really driven by data today. One of the very common platforms that you'll find organizations using to collect and report on data is something called the ELK stack. And the ELK stack is a combination of three different software applications. It's Elasticsearch, which is indexing, storing the data, and it provides a very fast search engine for data. And then Logstash. Logstash is a collection engine. Logstash is grabbing the data from our applications and grabbing these different data metrics from our infrastructure components. And then the last piece of the elk stack is Kibana. And Kibana is a graphical front end interface that provides what we call instrumentation, or basically it provides the pretty graphs and the charts, which allow us to view data and make sense of data on a more human level. When we're collecting data and we're making decisions on data in our DevOps organization, what we're trying to do is identify key performance indicators. And key performance indicators are really the most important metrics, most important pieces of data, which really just drive decisions within our IT organization. These KPI metrics could be business related metrics like how much revenue is our application generating, how many orders per day are we seeing, how many support calls are we receiving related to defects in our application. From an operations perspective, we might be looking at change error rates. We might be looking to see, how often are our build pipelines failing? How often are we, introducing defects? How many defects make it through our code pipeline out into production? And how many incidents are those defects generating? What is the uptime of our application, and what is the response time of our application? So we're oftentimes really focused on performance metrics. We're trying to delight our customers and ensure their happiness. And so we're looking at the performance and availability of our application. If our application isn't performing as expected, or if we're seeing some a decline in the performance or decline in availability, we might generate alerts to our development teams or operations teams to let them know that our application is having service health issues. One of the challenges that we have is, well, what types of things should we alert on? You could end up alerting on too many events, and then your team members are going to experience alarm fatigue because they're going to be getting alerts on their cell phone or in their email, about all kinds of different events, and then over time they'll just start ignoring events, and some of those events will be really really important. So the key is that if you're going to surface events and if you're going to alert staff, you need to make sure that the alert is not only important, but it's actionable in some way. Um, and we try to prevent alarms as much as possible. We try to build applications and infrastructure which is self-healing. We can, leverage things like auto scaling groups so that if a node in our environment fails, AWS will automatically replace that node with a new EC2 instance. We use elastic load balancers to distribute requests across a fleet of servers so that if one server fails, then the request can be redirected to other servers. We might use message queues um, to regulate the flow of work between our producers and our consumers. And we might spin up more consumers to handle a large backlog of messages. So we do everything we possibly can to make our environment and our application self-healing, to be very resilient, to be scalable, and to minimize the number of alerts that are generated out to staff members. And if you have an environment that's self-healing, there's no reason to generate an alert to somebody saying that a node has failed, because a failing node could be a very common event. And you know that you've architected your application in such a way and your infrastructure in such a way is that it will automatically resolve that issue for you. These metrics, as I mentioned, really drive decision making in DevOps organizations. The fact is that in every organization, you're going to have people with different levels of experience, and everybody perceives the world a little bit differently based upon their experience level and based on, just biases that they have. And traditionally, what you'd find oftentimes in organizations is that you'd have both experienced and unexperienced engineers making sort of educated guesses regarding technical solutions. Like an application would be experiencing a performance problem in an environment, and the engineers would kind of sit around the table and they'd be trying to think up ways to improve the performance of the application. And somebody would say, well, I think if we just add more memory to our servers, we can improve the performance of the application. And that might be true, but it's really sort of an educated guess. It's not one that has been, it's not like they've run an experiment or tested to see if that hypothesis is true. It's not that they're focused on gathering data to drive that decision making. It's really based upon past experiences and biases. In a DevOps organization, we fanatically collect metrics and we watch those metrics. We use those metrics to support our recommendations and our decision making. And any recommendation that is not supported by metrics and by data, we consider to be just simply a guess. And we treat it as a risky guess. So whenever possible, we try to use metrics to drive decisions. And the beauty of cloud computing and cloud infrastructure today is that it gives us a really inexpensive way to test out our hypotheses. If I want to test my environment on AWS, then I can use infrastructure as code to spin up a complete copy of my environment with my application running in it, and then I can simulate load on that environment using some sort of load testing tool and suite. And I can then capture and gather data from that environment to see if my hypothesis is true. And I can make changes to that environment to see how those changes might impact the performance. And then armed with that data, now I can go back to the team and the organization, and I can make recommendations which are solidly grounded in facts and in data. So wrapping up the lecture this week, I just have a few parting notes. First, you can't change a traditional organization into a DevOps organization overnight. Sometimes we call these DevOps organizations unicorns because they tend to be fairly rare. And what I've found over the past couple of years is that many traditional organizations are beginning this journey, and they're beginning to try to incorporate and embrace DevOps practices. And this journey is not something that can be, that can occur over the course of a few months. This is a journey which oftentimes can take years. And the hardest part by far of this journey is getting the culture right, is changing the culture. And this is very, very difficult to do in a traditional organization. It's easy to go out and buy software tools. It's easy to go and implement Jenkins and implement infrastructure as code tools, and you create scripts and build automation and all that. Anybody can do that. But changing the culture, getting people to buy into these practices, getting them to switch from long-running feature branches to continuous integration, to implementing code pipelines, to shifting left in their software testing processes, to embracing collaboration and transparency, to following a you know a design for operations methodology where developers attend operations stand-ups and operations people are engaged in daily developer stand-ups. These cultural practices are are difficult to implement because human beings are hard to change. Human beings are fearful of change. And so you have to begin, when you're introducing these practices, you need to begin introducing these practices incrementally and slowly. And over time, you'll gradually be improving your service delivery process. It'll gradually start speeding up over time. And it might take months, it might take a year or two, but as people look back in time, they'll say, "Wow!" They'll be really surprised at how how much that service delivery process has changed, how much has been automated, how much faster and reliable it is. But again, these changes do not take place overnight, and you have to be very, very persistent when you're working in an organization that is going through and starting to undertake this DevOps journey.